Hello everyone, I'm Shahd Mutaz, currently a year 2 student at the University of Sharjah, and today I'll be explaining absorption and secretion in the large intestine. So first let's orient ourselves on what is happening in the picture. So I've drawn a cell over here in black, and this side represents the lumen of the large intestine, while this side represents a blood vessel. And anything that is going inside the blood vessel to this side like this means that we are absorbing it, and anything going outside into the lumen means that we are secreting it. And as far as the cell membrane goes, we also have two different terms for each side depending on what it's facing. So the side facing the lumen is called the apical membrane, while the cell membrane facing the blood vessel is called the basolateral membrane. And you can simply remember it by that they both start with a B, basolateral and blood vessel. Okay, so before we get into the details, let's just quickly go over what is being absorbed and what is being secreted in the large intestine. Now, the large intestine's main function is to absorb water and electrolytes back into the body in order to prevent dehydration. So you can imagine that certain electrolytes will be absorbed, like sodium and chloride, while water is also being absorbed. On the other hand, we have things that are being secreted in exchange for what is being absorbed. So we have some potassium and we have bicarbonate ions, as well as some chloride will be secreted into the stool, but the majority of it will be absorbed. Now, potassium and bicarb are important components in mucus. Okay, so let's first start with sodium. Now, sodium, the first step in maintaining a concentration gradient and absorbing it is through the very famous sodium-potassium pump. And we know that the sodium-potassium pump is an active transporter, meaning that it uses ATP. So imagine that you are using ATP to actively transport 3 sodium ions outside the cell. So this is going to lead to a very high concentration outside the cell of sodium, of course, and a lower concentration of sodium inside the cell. So naturally, you're going to want to regain back all of these sodiums inside the cell. So we have 2 channels over here that do exactly that. So on the apical aspect, which is the side facing the lumen, we have a channel called the Na channel, or we can also call it the NaH plus channel because it's taking H plus out, which I'll get into in a minute. But we have the sodium channel bringing in sodium inside the cell. And this is termed as absorption because we're going like this, right? We're going into the blood vessel. And this is going to regain the sodium concentration inside the cell because all of the sodiums are going outside actively by the sodium-potassium pump. And also on the basolateral aspect, and it's important to know that this co-transporter in the large intestine is on the basolateral aspect because we do have this co-transporter in other areas of the body where it is on the apical side. But for now, just remember that it is on the basolateral aspect. Okay, so simply as we just said, is that sodium is being brought back into the cell in order to maintain some sodium inside the cell because a lot of sodium is being secreted out. And you can also imagine that since you have high sodium out, they're going to passively bring sodium inside the cell down its concentration gradient. So it all makes sense if you understand it rather than memorize it. Alright, so now we're done with sodium. Let's talk more about bicarb and H+. So let me bring your attention to this very famous equation. So we have water and carbon dioxide, which are metabolic end products, and they're going to be converted by carbonic anhydrase to carbonic acid, and which will further dissociate into hydrogen ions and bicarbonate ions. So imagine that right now, because of this equation, you have a lot of these two inside the cell. So we have a lot of H plus and a lot of bicarb inside the cell. Okay, so naturally, simply by going with the fact that anything would like to move along its concentration gradient, meaning from high to low, so naturally, we're going to want for the bicarb to leave the cell and for the H plus to leave the cell. And this is where over here the H plus is going outside while the Na is going back into the cell. So we call this an antiporter because something's going out while something else is going in. Same thing over here. We have bicarb leaving the cell, and since something negative is leaving the cell, we need something negative to enter the cell one more time. In this case, it's going to be chloride. So chloride is being absorbed back into the large intestinal cell, which will be eventually by other channels, which are not drawn here, which will be eventually absorbed back into the large intestine, into the blood vessel. Okay, so now you're going to be asking as to what is this doing here. This is what I previously mentioned, that some chloride ions will be secreted. Now we have this CTFR transporter, or the cystic fibrosis transmembrane transporter. And what it does is that it takes some chloride out. And honestly, the way I remember it is that you need to maintain some chloride out in order to eventually bring it back into the cell in exchange for some bicarb. So you can't have everything going in one direction, because even the sodium isn't going in one direction, because then how will you regain the concentration gradient? So that's why you have different channels doing different things for one ion. But it's important to know that the net, or the majority of chloride, is going to be absorbed. All right, so now let's go into the last electrolyte, which is the potassium. And the potassium, as we said, will be secreted. So over here you have the sodium-potassium pump. It is bringing chloride outside from our body, outside from the blood vessel, into the lumen, eventually going out from here. And also you have some of the potassium also going through the NKCC co-transporter. At the same time, as we previously mentioned, you need to have a channel that maintains some of the concentration gradient. And in case we ever are in a clinical state where we have hypokalemia, for example, we will need to absorb back some of the potassium. So this is why we have another potassium channel on the basolateral aspect, which also absorbs some of the potassium. Okay, so, as I said, the important thing to know is that the net, or the majority of the potassium, will be secreted. And this is why in cases like diarrhea, where you have increased potassium secretion, you're going to be left with hypokalemia, which is a state of low potassium. Okay, so now we're done with the ions. I just want to bring your attention to something very important related to aldosterone. Now, as we know, aldosterone absorbs absorbs sodium into the cell or into the body and secretes potassium. And the way that it does this is by increasing the synthesis of this channel over here, the Na, or the sodium channel. Now, by increasing the synthesis of this sodium channel, you're going to be taking more sodium inside the cell. Okay, from the lumen, from the stool, you're going to be taking more sodium inside the cell. Now, since we have high sodium inside, high over here, now we're going to be activating the sodium-potassium pump. So more sodium will thereby be going through this channel. So the net product is more sodium being absorbed while more potassium being secreted. So this is going to be activated, so more potassium is going this way, eventually going outside into the lumen. And this can also lead to hypokalemia in certain pathological diseases in which you have a high aldosterone. But in order to maintain, in normal people, in order to maintain a normal electrolyte balance, this is what happens when aldosterone is being secreted. So very quickly, just to sum up, we have absorption of sodium by these channels, absorption of water, which is obviously going to follow sodium. Now, as we know, that water always follows salt, and in this case, it's following the sodium and the chloride. So that's why water is passively being absorbed back into the blood vessel. And that's it. If you have any questions, let me know in the comments or contact me directly. I hope this made sense to you, and goodbye.